Hi, I am Sanjay Patel. In this lecture, I am going to discuss two problems on double integral. One problem is a nice problem of change of order of integration. Another problem is an application of one result which we have mentioned in our previous videos. So let us start with the first one. Change the order of integration. Change the order of integration for this x is equal to 0 to 2a, y is equal to square root of 2ax minus x square to square root of 2ax, f of x comma y dx comma dy. So first of all, note that the limits of integration here are x is equal to 0, x is equal to 2a, the curve y is equal to square root of 2ax minus x square, and y is equal to the curve square root of 2ax. Let us understand what are these curves actually. So I will be writing this way. Say for this curve, for y is equal to square root of 2ax minus x square, I can write as y square is equal to 2ax minus x square, which we can simplify further as x square minus 2ax plus y square equal to 0. This is something like circle, and if you want to see what is the center and radius of this, let us write it as a sum of two squares, like the standard form. To make this perfect square, I should add a square and also subtract a square. So let me write this way: x square minus 2ax plus a square, and this I am writing as y square, as it is an a square, adding a square on both the sides. So this gives me x minus a whole square. This y square I can write as y minus 0 whole square, and this I can write as a square. So it is a circle with the center a comma 0 and radius small a. Okay. On the other hand, the second curve, y is equal to square root of 2ax, you can write as y square is equal to 2ax. So it is a parabola. This is a parabola. Okay. And for both the curves, we want to find the intersection of these two curves with the given limits or this given lines x equal to 0 and x equal to 2a. So for this circle, when x is equal to say 0, putting x equal to 0 in any of this, say in this, we get y is equal to 0. Okay. And when you put x is equal to the second limit, that is 2a, put x equal to 2a in any of these equations. Say if you put here, it is 2a into 2a, that is 4a square, and minus 4a square. So we'll get y is equal to 0 again. So the points of intersections of the two lines and the given circle are 0, 0 and 2a comma 0. Here on the other hand, if you want to find intersection of this parabola with these two lines, we see that when x equal to 0, it gives us y is equal to 0 by putting x equal to 0 here, and when x is equal to 2a, we will get y square is equal to 4a square. Putting x equal to 2a here, 2a into 2a is 4a 4a square. So y will be plus or minus 2a. Okay, so we get this 2 points, 2a comma 2a and 2a comma minus 2a as the point of intersection of this parabola with these lines. Okay, so let us draw the figure for this region of integration. First, let me draw the x-axis and y-axis. So this is y-axis. And the x-axis is say this line. This is x-axis, this is y-axis, and this is origin. And first of all, I will draw the circle. The circle has the center, remember now, as a comma 0 and the radius is a. Center is a0, that is on the x-axis, and the radius is a. So I can take a and a comma 0 somewhere here. Suppose this distance is a and its double is this 2a. Let us draw a circle somewhere here. Circle say with circle with center is a comma 0 and so let me draw a circle like this. Okay, fine. So the center is a0 and radius is also a. So this point, this is a, this is the center. Let me shift it here. This is the center of the circle, which is a comma 0. The radius is a, so this is a and this is also a. So the total length is 2a. So this point has the coordinates 2a comma 0, and this circle equation is x minus a square plus y square is equal to a square as we have derived. And the second curve is the parabola. Y square is equal to 2ax, so it is symmetric about x-axis because replacing y by minus y, equation is not changing. So y square is equal to 2ax is this parabola. Let me draw like this. Let me shift this a little bit. Okay. So this parabola is something like this. Okay, and also it goes on the other way. So this is the parabola whose equation is y square is equal to 2ax. Okay, remember that the line x equal to 2a intersects the parabola at 2 points, 2a and minus 2a. So if this is a, let me draw the radius so that you can understand. If this is the radius of the circle and this length is a, so the corresponding point somewhere here, so that is a. If I take the double of the distance, say somewhere here, this is 2a, and somewhere here, say this is minus 2a. Okay, and this parabola is intersecting with this line passing through 2a comma 0 like this. So it is intersecting this way. Let us shift it somewhere here. This is not coming now. Let me do it again. Yes. So this line is the line x is equal to 2a passing through this. And it is intersecting this parabola at the point say 2a comma 2a. So this is the point 2a comma 2a, and this point, this distance is 2a and this distance is also 2a. So it is 2a comma minus 2a towards the negative y-axis. Our region of integration is the area between the limits or the curves x equal to 0, that is y-axis, x equal to 0, x equal to 2a, this parabola and this circle. So this is the region of integration. This is the region of integration. Okay. What is given to us is the double integral with respect to, say, y first. Let me write it so that you can look at this double integral and see what happens. X equal to 0 to 2a and y is equal to square root of 2ax minus x square to square root of 2ax, f of x comma y, say dx comma dy. So first it is integrated with respect to y and then with respect to x. We want to change this order. For changing the order of integration and integrate with respect to x first, we have to look for an arbitrary strip in the region of integration. This is our region of integration. If I take a strip parallel to x-axis, and then for all position of the strips, if it is here, then the left hand curve is this parabola, right hand curve is the circle. If the strip is over here, then the left hand curve is parabola, but the right hand curve is this straight line. And if the strip is taken here in this portion of the region of integration, then the left hand curve is circle and right hand curve is straight line. So you can see that there are three places at which we are getting different curves for the endpoints of the horizontal strip in the region of integration. So we have to divide the whole region in such a manner so that we get a nice or regular region in which we can have the same end curves for all the strips in those regions. See, if you observe carefully, then if I consider a line which is passing through the point this, that is the point 0 comma a, and parallel to x-axis, then that line is touching. Okay, it's not proper. That line is touching this circle. It is tangent to the circle at this point. Okay. It is not still touching this properly. Let me take it again. if I take a line passing through this and touching this circle in this manner, I will change this a little bit. Okay, fine. Let us call that as point A. Let us change this. This point is A. So the equation of this line is y is equal to A. So if you take this line and divide the whole region in, then the region is subdivided into 3 sub-regions. One is this, it is E1, other is E2, and the third one is E3. Okay, that is the important thing here. We want to write the limits of integration for each of this region in the new order. So let me first of all write this is equal to double integral over E1 f dy dx plus double integral over E2 f dy dx plus double integral over the third region E3. This is not double integral over E3 f dy dx. So we are integrating with respect to x first now in all these 3 regions. So you must consider a strip parallel to the x-axis. If you take a strip parallel to x-axis here in the region E1, the left-hand curve is this parabola, and we have to express the equation of this parabola as a function of y. So from this I can write x is equal to y square by 2a. So equation of this parabola is x is equal to y square by 2a, and equation of this circle. Now understand what is this circle. It is given by x minus a whole square plus y square is equal to a square. This circle I can write as x minus a square is equal to a square minus y square. I want to write x as a function of y, so I will get x minus a is equal to plus or minus, let me write plus or minus square root of a square minus y square. Okay, taking square root on both the sides. So we have 2 equations here. X is equal to a plus or minus square root of a square minus y square. So the circle equation in as a function of y, x as a function of y, are given in 2 ways, a plus this and a minus square root of a square minus y square. So which equation is to be considered? X is equal to a is here, so this distance is x equal to a, okay, and a plus something will come here on this part. So the equation of this circle is x is equal to a plus square root of a square minus y square. So for this arc from this point, this critical point, from this critical point to this point, the equation of this part is x is equal to a plus square root of a square minus y square. On the negative side, the equation of this part of the circle is given by x is equal to a minus square root of a square minus y square. So for the region E1, if you consider a horizontal strip to integrate with respect to x first, the left hand curve is on this parabola, which is x equal to y square by 2a, and right hand curve is the circle given by this equation. Okay, so I can write that this is equal to x is equal to parabola, which is given by, say, y square by 2a, x is equal to y square upon 2a. So you want to go from this blue curve to the pink curve, which is a circle. The circle equation is this. So we write x is equal to a minus square root of a square minus y square f of x comma y dy dx. And for the limits of y, which are constants, we have to find the minimum and maximum value of y in that region E1. This is our region E1. This is our region E1, which is between this circle and this parabola. So in this region, when you enter the region, the minimum value is somewhere here on this origin, that is y equal to 0. It is this, and the maximum value is obtained at this point when you exit the region through this line, that is y equal to a. So the region E1 is bounded between y is equal to 0 to y is equal to a and the two curves. So the limits of y is 0 to a. This plus for the second region E2, let me write here, for the second region E2, again we have to write limits of x and y, f of x comma y dy dx. So for E2, we take a straight parallel to x-axis, this is E2 here, and on this straight, the left hand curve is again this parabola, which is already written here, x equal to y square by 2a, and this is x equal to 2a. So it is very simple, x equal to y square by 2 and x is equal to 2a. Okay, and for the region E2, the minimum value of say y, when you enter in the region, it is on this line. If you move in this direction, the first point when you enter in the region E2 is on this line, and on this line the value of y is a, and when you exit the region, the last point is this. So this is the line y is equal to 2a. So the region E2 is bounded between y is equal to a, y is equal to a, and these two curves. So y varies from a to 2a in this. Y is equal to a to 2a plus the last region, again x limit and y limit, f of x comma y, say dx comma dx into dy. So first with respect to, sorry, I have made a mistake here. Let me change this and this also. We are changing the order in the other way. So it is dy dx. These are the limits of x and limits of y, which are constants. So for the region E3, which is this part, bounded between this circle, whose equation we have already written, it is this, and say this curve, that is line, this line is given by x is equal to 2a. And for limits of y, so when you enter in the region, you have to enter through this point, and the value of y is 0, and when you come out of the region, the maximum value of y is here. So you can say the region E3 is bounded between y equal to 0, that is this x-axis, y equal to a, that is this pink line, the circle, this arc of the circle, and this yellow line, that is x equal to 2a. So x equal to the circle to the line, x equal to 2a, and the circle equation in this case we should take as a plus square root of a square minus y square. Okay, x is equal to a plus square root of a square minus y square, and x equal to 2a. Y varies from, in the region E3, y varies from this point to this line, so 0 to a. Y varies from 0 to a. So this I can change the order of this integration. So this is a little bit difficult and nice problem. And let us consider the next example now. So the next problem is evaluate the double integral of the function e raised to x plus y over the region E, where capital E is the region lying between, is the region or area, say lying between two squares lying between two squares of sides 2 and 4 units and having center at the origin, and the sides of the square and the sides of the squares are parallel to the coordinate axis. So there are two squares, and one is of side whose length is 2 and the other is of length 4 units, and we have to consider the area between these two circles. So let me draw the two squares first. Say one square is this, okay, and another square, let me this is one square, and another square which is this. Okay, and both the squares have the sides parallel to the coordinate axis and having center at the origin. So I will take one axis like this and another axis, that is y-axis, not this way, y-axis somewhere like this, and let us move this. Yes, so these are the two axes, x-axis, y-axis, and this is origin. And our region of integration in this problem is the area between these two squares. The outer square is this pink and having the side parallel to the coordinate axis with length 4 units. The total length of this, each of the side is 4. So this much distance is 4. So I can take this point of intersection as, so this is 4 comma 0. This you can write as sorry, not 4 comma 0. It is half of that, because the total length is the whole length is 4. So half length, which is exactly 2 comma 0, and this is minus 2 comma 0. So this distance is 4. Same way, this point is 0 comma 2 and this is 0 comma minus 2. The smaller square is of side having length say 2 units. So half is 1. So this point will be 1 comma 0. This point is minus 1 comma 0. Same way, this is 0 comma 1 and this is 0 comma minus 1. And the region of integration is the area enclosed between these two squares. And we want to find the value of the given double integral over this region. But you see, the regions are not, this region is not regular, and if you divide it, then one has to integrate over many subregions and then add them all. But instead of that, we can use one result which we have written in our previous lectures, and that result is something like this. So I am just reminding you, recall that if we have E1 is contained in E2, okay, E1 is subset of E2, then the double integral of a function f over the region E2 minus E1 is equal to double integral over E2 minus double integral over E1. So I'm going to use this result which we have discussed in our earlier lectures. So I will be taking the smaller square as E1 and the larger square as E2. So let me put this way. Consider, say, I1 is equal to the integral over the smaller square say E1 of side 2 units, okay, and I2 I am taking as the same thing, integral over the larger square, integral over the larger square, E2, having side 4 units, okay, having side 4 units. So this larger square is E1, E2, and the smaller square is E1. So we will find the integral of the given function, which is e raised to x plus y, over both the squares, and then subtract the integral over the larger square minus integral over the smaller square. So we have to do two parts. So first, part 1, let me write like this. So first part, that I1 is equal to the double integral of e raised to x plus y dx dy over the square E1, where E1 is this square rectangle, you can say, having side this x equal to minus 1, y x equal to plus 1, y is equal to say minus 1, and y is equal to plus 1. These lines you can write as x equal to minus 1, and this is x is equal to plus 1, and this is y is equal to minus 1 and y is equal to plus 1. So it is very simple integration. Integral over this region is given by this is equal to integral x is equal to minus 1 to 1 and y is equal to minus 1 to 1 of e raised to x plus y dx into dy. Okay, it is a rectangle, so and function is integrable. So in whichever order you integrate, you will get the same value. To integrate this, first with respect to say y, I can write like this: x equal to minus 1 to 1, and then y is equal to minus 1 to 1. This I can add as e raised to y into dy, and e raised to x is constant when you integrate with respect to y, so we can put it outside of the integral sign. And x equal to minus 1 to 1 e raised to x. Integral of e raised to y is e raised to y, and one has to put the limits minus 1 to plus 1, and then dx. So it is a very, very simple integration, and the problem also becomes very easy. So this is equal to minus 1 to 1 e raised to x, and this is nothing but e raised to 1 minus e raised to minus 1 dx. So this I can write as e minus e raised to minus 1 as a constant outside, minus 1 to 1 e raised to x dx. And this integral is also same thing as the previous one. This is as it is, and integral of e raised to x is e raised to x and minus 1 to plus 1. So we get e minus e raised to minus 1 into say e raised to 1 minus e raised to minus 1. It is in fact e minus e raised to minus 1 square. Let us call this as result number 1. And for the second integral, that is I2, this was I1. So I2 is the integral over the larger square, which is E2, double integral of the function e raised to x plus y dx comma dy over the larger square e2. And that is very simple again, because the larger square is bounded by this 4 lines. One is x is equal to minus 2, this is x equal to plus 2, y is equal to minus 2, and y is equal to plus 2. So I can write the limits of integration directly and compute this integral as the part 1, that is x equal to minus 2 to plus 2, y is equal to minus 2 to plus 2, and e raised to x plus y dx into dy. So it is minus 2 to plus 2, and this I can write as e raised to, say, we are integrating with respect to y first, e raised to x is constant, integral y equal to minus 2 to 2 e raised to y dy into dx. So it comes a similar thing, except the limits are different numbers. So I am writing minus 2 to plus 2 e raised to x, and integration of e raised to y is e raised to y, and minus 2 to 2 dx. You know, this is e raised to 2 minus e raised to minus 2, which is constant. I am writing directly e square minus e raised to minus 2 times this is x equal to minus 2 to plus 2 e raised to x dx. So this will be left after 2 steps. And this is again, you will get the same value. If you integrate this, e raised to x integral is e raised to x, and the limits of integration are minus 2 to plus 2. So we get the same answer, e square minus e raised to minus 2, e square minus e raised to minus 2, which is equal to e square minus e raised to minus 2 whole square, and this is my result number 2. So therefore, the required double integral over the given region E of e raised to x plus y dx dy is equal to double integral over e2 minus double integral over e1 of the same function. I am not writing everything, it is understood, and this is nothing but the value, say, I2 minus I1. And what is I2? It is e square minus e raised to minus 2 whole square, and this is e minus e raised to minus 1 whole square. So if you simplify this, what you will get is just it's a difference of this 2 power of x squares. Can simplify this manner. Say this is okay. So this is e minus e raised to minus 1. I can take as e square. Or let me write this way. Yes, e square minus 1 upon e square whole square minus e minus 1 upon e whole square. Just a matter of simplification. One can expand directly also, and this I can write as, say, e minus 1 upon e whole square into e plus 1 upon e whole square. A square minus b square you can factorize as a minus b a plus b minus e minus 1 upon e whole square. So e minus 1 upon e whole square is a common factor. What is left inside is e plus 1 upon e square minus 1. So this is our final answer. You can simplify and write it as e minus 1 upon e whole square into e square plus 1 upon e square, and the middle term is 2 minus 1, that is plus 1. Okay, so this is my final answer. So this is a nice problem, an application of that special result, integral over a larger area minus integral over a smaller area. So this is about different ways of computing double integrals and changing the order of integration. So these are very, very important topics. So in the next lecture, we are going to start, say, the concept of triple integral and see how to compute the triple integrals. Remember, the double integrals are defined over an area, while triple integrals will be defined over some volume. It is a three-dimensional, say, integration, and you can see that the given region of integration is some volume. We'll discuss that interesting topic in our next lecture. Till then, goodbye. Thank you so much.